sure there's a saying in English, but happy lunch. Okay, so I will talk about the equivalence principle and our atom interferometry experiment. In this experiment, we have two species of atoms, and they're very well overlapped, and we monitor while they propagate in space. We try to shield the atoms from any known physical influence, basically. And if we manage to do that, then we will be sensitive to any unknown physics, basically. So unknown fields or some perturbations of the equivalence principle. So some people might say that the Heisenberg uncertainty principle is counterintuitive because it doesn't really map well to everyday life. But what about the equivalence principle? So I think the equivalence principle also is quite counterintuitive. And I will explain in a second. So what does the equivalence principle say? It just says that gravity disappears locally. So if you think about a geometric theory of gravity, this is just a trivial statement. So you will not learn anything about the geometry if you only look locally in a small region. This is just a trivial statement. However, if you look at little Isaac, he drops the apple and sees the acceleration between him and the apple. So you wonder, and this is a very local measurement, obviously. How does that relate to the equivalence principle? So,
is there, does someone have like a, it's working this
I think it's Zoom on mute. Someone got their mic on.
Okay, can you, if you're on Zoom, can you mute your, just
Oh, and you.
there's some issue with sound.
The sound?
Some sound feedback.
Okay, I'll check.
okay, so little Isaac does this very local experiment. He drops the apple and he sees the differential acceleration between them. So how does this come together with the equivalence principle? So gravity does disappear locally. However, what does not disappear is electromagnetic forces. So Isaac obviously stands on some ground and is constantly an electromagnetic force. And this is just our everyday life. We always live in a situation where we have this acceleration bias. So we assume this bias, this acceleration just to be normal, and everything on top of that is kind of a physical effect. Which is obviously why the equivalence principle is counterintuitive. However, if we would live in space, probably the equivalence principle would be something very natural, and we wouldn't think about it too much. Okay, so what we do with our experiment is we create a local probe. And this local probe, we hope, is sensitive to some local field, for instance, that we have not heard about yet, or that we have not detected yet. Another thing, obviously, if you do a local probe, you will be insensitive to gravity, which is, in a sense, a feature, because gravity can be a noise source. I mean, mostly it is. So what we want from our local probe is we want it to be insensitive to, in our case, to differential velocities and differential positions of our atoms, so basically initial conditions. We will try to do a good job by making the experiment insensitive to those parameters, because we're interested in some local unknown field. Okay, so why are atoms good probe particles for all kinds of measurements? So the first thing is you can isolate them very well from any conventional disturbance. That works really well. And the more important thing, though, is that you can manipulate and read them out with accurate lasers. So this is something unique to atoms, which is not possible with macroscopic objects. You cannot really manipulate them very well with accurate lasers. This is way harder. Another thing is that you can overlap atoms pretty well because they're just pretty small. Okay, so if you compare that to non-local probes, you have two parts, two probe masses or probe particles, and that's separate by large length scale. In this case, you obviously can measure a lot more things than what you can do in a local probe. For instance, you can measure gravity, but also you're sensitive to gravity and noise. Okay, so just this. Yeah. So typically, a local experiment is just way easier than a non-local one. Okay, so let's take a quick look at how atom interferometers work. So typically, you have a symmetric pulse sequence. So in this case, we have three laser pulses. Those are just standing waves that split the atoms into superpositions of momentum states. And by doing that and waiting for some drift time, they will separate in space. The two parts of the wave function, you will create some spatial superposition states. So important points here are the following. The momentum superposition is created in a certain direction, which is given by the wave vector of the standing wave. So this not only has a magnitude but also a direction. It's a vector, obviously. Right. And you have, in this case, you have three of them. So all three of those vectors can have different magnitude and also different direction. Okay. So you split. You have your interferometer. It opens up and it closes again. And at the end of the interferometer, you look at the atomic population in the output ports. In this case, for instance, if you do it with a single atom, it will pop up in one of the ports. If you do it over and over again, or with an ensemble of atoms, you will maybe see certain population distribution. In this case, you have the atoms in the two ports, fewer up than lower down. And by normalizing those populations, you can write it in terms of a phase phi. So this phi is the interferometer phase. So this is how you get the interferometer phase from the experiment. How do you calculate the phase? How do you give meaning to this measurement? It's actually very easy for most cases. It's simply just a sum, appropriate sum of all the positions of the atoms at the laser interactions and the k vectors. So this is actually very simple to compute. And somewhat famous, the biggest typical phase shift you will have in interferometer. So you say the phase shift is big, although it's not really there because the compensated is kgt squared. So what are the numbers for k? So k is the phase vector. If you do some more complicated pulse sequences, you can increase k to 10 to the 8 or 10 to the 9 per meter, which corresponds to wavelengths of hundreds of nanometers, all of them, tens of nanometers. So the nice thing about, so why you would want to use an interferometer is because you can prepare and read out with this very fine laser. So you can measure in the end position differences with very high resolution. So on the order of nanometers. Okay. Let's take a look at what we want to measure. So what we want to measure is the differential phase between the two interferometers, one for 85 and one for 87. So since we're looking for small things, so we are trying to be isolated from all known things, the phase shift between the two interferometers can be small, right? So, and we also want to be able to measure small phase shifts. And especially, it might be smaller than your phase noise. Phase noise just means what the fluctuation of phases is you measure between different runs of the experiment. So here in this case, you have 4 ports. So the upper 2 ports are rubidium 87, the lower 2 ports are rubidium 85. They have roughly the same phase, as you can see in the population distribution. So how do I get the differential phase out from that? So if I plot the population versus the phase, you will see that for some population ratio, you can infer different phases. And this is not a big issue at first. The main problem is that you cannot distinguish whether 87 has the higher phase or 85 has the lower phase. So you can infer just different phases from this one result. So this is a slight annoyance. The real problem though is that if you want to average multiple measurements and your noise is bigger than the difference between those two things, then you won't be able to average them down because you don't know what the sign of the other one is. So if the difference between those is large enough, you always assume that the phase is just this difference. So it's large and the fluctuations on this large effect are small. So you always say, oh, the phase is this particular number. For small phases, that's not possible. Okay. So small differential phases cannot be resolved easily, and this is very analogous to just the diffraction limited resolution. That if you have two spots close to each other and the area is bigger than the separation, it's just hard to distinguish the photons coming from the two sources. Okay, so how do we solve this problem? So we really want to measure the small phase shifts. So what we do is we open up our interferometer. So what it means is that there are various ways to do that. Basically, the atom interferometer doesn't close fully anymore, but there will be some slight openness to the interferometer. What does this create? It creates sensitivity to initial conditions, which is obviously a bad thing. But what we will gain in exchange is we will get the slope of the phase. So if we go back, we will just see what the slope is around some average phase. It will be easy for us to distinguish whether we're on the left side or on the right side. We will know the sign of the phase. Okay, so what do? We actually do a two-dimensional open interferometer. So we slightly change the angles of our interferometer beams such that there is a phase shift in the horizontal direction. So there will be a horizontal momentum difference, and that can be seen in a phase shift across the horizontal direction. So what you can see here is the upper two parts are rubidium 87, lower two parts are rubidium 85. You can see a sinusoidal modulation of the population. And in this case, it's very easy to compare the phases because you just have signs and you compare the relative position between them. So in this scheme, we can resolve the differential phase. But as pointed out before, this creates problems as well. Okay, so how does our interferometer look like roughly? So we launch them in a fountain geometry, so basically they just go up and down. They don't quite go up and down because the Earth rotates during our measurement, so the trajectory is not fully straight in a sense in the lab frame. So we launch them up and down. They're very well overlapped, and after some time, we delay the imaging of one of the two clouds so we can take a picture where they're spatially separated. So they're only spatially separated after the interferometer. During the interferometer, they're very well overlapped. So 87, 85. If we do multiple shots, the overall phase of the interferometer will change, but the differential phase between those two will have some much smaller phase noise. So in this case, 16 milliradians. And this corresponds to an acceleration of 3 × 10⁻11 Gs per shot, which is somewhat better than previous full species experiments. So that's okay. So now to the big problems, or basically what keeps us up at night, is systematic errors. So the more important systematic errors, I would say, are just the ones related to the differences between 85 and 87. So what degrees of freedom do we have to worry about? So we have horizontal velocities in two directions. We call them east and north, and also position. And those couple to certain other effects to create phase shifts. So as mentioned before, we don't want to be sensitive to anything other than unknown stuff. So we have to take care of those. So what do they couple to in the horizontal case? Mirror rotation. So if you have different velocities of position, then it will look as a different phase in the final image, depending on where the mirror rotates. They have mirror curvature, which is just means that the mirror where the beams are reflected off of are not flat. That creates some horizontal phase shifts. The fringe reimprint has some angle that creates problems. optical forces can couple to those parameters, and maybe even horizontal correlated gradients. We haven't really seen that yet. Okay, so just from the sheer number, you can see horizontal is our biggest nightmares, basically. On the other hand, vertical problems, which just scale with the vertical velocity and position, they're mostly coupled to gravity, just because they're displaced in space, so it's not perfectly local, basically, and the tuning phase shifts. The good thing about those two, and I will talk about it in a slide in a second, is that we can control those very well. Even though those are the biggest phase shifts, the gravity ones, we can control them so well that it's not a big issue for us. So what are other differences between 85 and 87? Obviously, they have different mass, which leads to a different recoil velocity, which then again leads to different vertical position and velocity. So it kind of reduces the local, so how locally your experiment is, because we have different velocities in the interferometer, and it's just impossible to perfectly overlap them. But with our geometry, we just try to do a good job doing that. And what else is different? The optical spectrum is pretty similar, but slightly different. That creates problems. So if they are both in some laser beams, they will basically experience different optical forces, which is basically the same thing as radio frequency. So then the next thing is magnetic moments. So we prepare them in magnetic insensitive states, but they have a slightly different second order Siemens shift, so the magnetic moment is not the same. And that couples over magnetic field gradients to phase shifts. This is also a problem. Okay, so what do we do to tackle those problems? So we have the golden strategy is twofold. First of all, I mean, it's very obvious things. You just minimize the differences. So you just try to overlap them very well as best as you can. But this is really only one thing. The other thing is you try to engineer the interferometer such that they are just not sensitive to these parameters. And the really great thing, as we will see in a second, is that when you combine those two effects, you don't have to do a good job with either of those. But if you do a decent job with either of those, they just multiply, and you get a big reduction in sensitivity. Or in errors, that's not sensitivity, a big reduction in errors. Okay, so first, briefly look at the vertical position and velocity issues. So we have our two interferometers in blue and in red, rubidium 85 and 87. So they're displaced by some amount because they have different parameters, so we will not be able to prepare them perfectly initially overlapped. And so the first thing we need to do is to minimize the position is measure the distance. So what we do is we just change slightly the wavelength of the middle laser pulse to measure the distance. And then in the next step, we just manipulate them before the interferometer such that they overlap at this displacement we just measured. So in this way, we can just overlap them somewhat precisely. But on the other hand, the other thing we can do is we can suppress the sensitivity. How do we suppress the sensitivity? Before I come to sensitivity, I also like to point out the upper graph, where you can see the phase shift for different displacements as a function of frequency. So the other thing is we want to suppress the sensitivity. So what do? We not only add this little wavelength change to the middle pulse to measure the position, but we just add just enough that it exactly compensates for the gravity gradient. So what we do is we measure the gravity gradient and then just put in this frequency change in the middle pulse just to compensate it. And if we do a good job, as you can see in this phase formula here, when this delta k equals this other term here, then you will end up just with quadratic errors. You will have an error in the displacement, you will have an error in your gradient measurement, and this is the ideal situation you want to be in, quadratic and errors. So by combining those two, you will reduce the error by 4 orders of magnitude, which is for our current goals. I mean, we could easily improve it also to 10 minus 13 G level. Okay, so horizontal problems. One thing is obviously that the Earth rotates quite a bit, rotates pretty fast. So if you do if you don't move the laser beams on your own, then just let gravity rotate them, you will see a picture like this. So here it's just one species, and you can see quite high frequency fringes across the cloud. And with this kind of picture, we can determine the Earth rotation to 3 orders, like 10 to minus 3, few times 10 to minus 3. So in order to get rid of this phase shift, because it couples to horizontal positions, we have to compensate this effect. And so basically we need to know where gravity is, where the rotation axis is to 0.5 milliradians. And also have to keep the horizontal position small. The rotation of the Earth is constant, so the rotation angle between the different laser pulses is the same. And this is what we call a velocity fringe. This couples ideally only 2 velocities. But the other thing you can do is make a position fringe, which where the angle is only changed for the first pulse and not for the second, for the other two. And having those two schemes, basically, we can just test for sensitivity to both velocity and position horizontally. And when you change it with the separation horizontally, you can measure all different kinds of phase shifts. It's a little bit complicated, but this is just the way we calibrate whether we do a good job suppressing horizontal errors. Okay, so then quickly I'll just mention what we do to the optical spectrum. So the optical, the resonances of rubidium-87 from the F2 to the higher states and F3 of 85 to the higher states, they're separated by 1 gigahertz. And we use those 2 ground states just because they are the closest in frequency. So when we apply our laser pulses, specifically we apply the Bragg pairs for doing the interferometer transitions, they will see very similar forces. So and a very important thing is that we also add a compensation pair. So we basically add so frequency components that do not drive transitions, but apply opposite optical forces to the Bragg pair. For all the pulses that are off resonance, you can with this you can cancel out. But you can reduce the optical forces by a lot. And the reason they're opposite signs, the optical force, is just because one of them is reticule and the other pair is fluid. So one of the still a little bit problematic for us is the control of the carriers. Because the carriers are very close to the resonances, so you want them to be very small. But this is a little bit of a problem for us. So I'm finished. So this is the team. We have the boss Mark, Min, and Chris. So Min, a new PhD student, Chris, a veteran. Yeah, and also on the plot we have our very latest data. Here you can just see a longer run of many shots. So this is 300 shots in 2 hours. As you can see, most of the shots are very nicely distributed, like you would expect from noise, from statistical noise, or from Gaussian noise. But we have this weird lower end tail that we don't quite understand yet. So this is what we are exactly trying to figure out right now. But apart from this little tail, the shape looks very good. Thank you.
Well, if you were to discover there was some sort of difference between the two, like, are there any interesting models that would inform?
I'm not really an expert on any models. I mean, there are lots of quantum gravity theories kind of based on violations of the equivalence principle. So that's something you can test. Yeah, I'm not so. I mean, then there are proposals about, I don't know, unknown fields, dark matter, for instance, and we would kind of be sensitive if it interacts differently with 85 and 87. maybe it interacts more with the two extra neutrons or something. That's what you would potentially do, and you would maybe see some change over time, over years or during the year, something like that. Yeah, but yeah, I would say it's not very bounded. It's pretty open what you would test and how would you test.
Any other questions? So maybe, yeah.
So when you don't close your interferometer, I sort of think you're changing from doing homodyne to heterodyne. So then you suffer a little bit on signal. So is there a very fine-tuning angle where you tune the angle where you close the interferometer to reduce the sensitivity, but also balance the sacrifice on the signal? Is there a sweet spot?
Yeah, so I think the sweet spot is basically that you only open in the direction you see and not in any other direction. So if you only open in the one direction you can clearly see, it is not a big issue, basically. But the other ones are closed. So what you don't see, you have no sensitivity, or there's no problem in the other direction you don't see. And it's actually what we do. So the fringes are supposedly very well aligned with our camera. And on the camera, the phase shift itself does not present a big issue, because you can compare them very well.
Okay, so maybe we can.
Yeah, but it's actually an interesting analogy because you also lose some sensitivity going heterodyne from homodyne. Yeah. It fits also here, because you explore all the phases which can have lower signal noise, or will have lower signal noise.
Thanks for having me, and thanks for coming. So my name is Will, I'm the group of Benjamin Lett, and today I'm happy to share with you the latest result from our discrete Gaussian quantum simulation experiment. So first, why is this Gaussian interesting? In the early days of quantum simulation using ultra-covalence, so typically people would pick the group 1 elements. So these alkalis feature one single valence electron in the s orbital. On the contrary, this Gaussian is a lanthanide in the transition metal series. So if you study its ground state electron configuration, it has an orbital quantum number of 6 and a spin quantum number of 2. So this high angular momentum in the ground state leads to a very large dipole moment of about 10 Bohr megaton. So if one considers the pairwise dipole-dipole interaction energy, that would be about 100 times that of your typical alkali, which gives us one more knob to tune to stimulate interesting Hamiltonians. So from classical EMM, we know that the dipole-dipole interaction, so from now on I refer to that as DDI for short. So it is long range in that it depends on 1 over interparticle distance u, is also anisotropic in that it depends on a geometric vector v of theta, where theta, as shown in the cartoon over here, is the angles obtained by the dipole polarization, as well as the displacement vector between our two dipoles. So in our typical quantum simulation experiments, we care about three extrema dipole polarization. So first, we have the theta equals 0 degree, or the head-to-tail configuration. That would give us the maximally attractive DDI. Second, we have the magic angle, which is the 55 degree. So this would effectively make the V of theta factor vanish, so turning off the DDI. Lastly, we have the theta equals 90 degree, or the side-by-side dipole configuration, which would give us the maximally repulsive DDI. So now I will provide you with some highlights of the project that I'm going to tell you today. So I will present the first experimental study of a Luttinger liquid with both contact and dipole-dipole interaction. So we realized this by trapping dysprosium Bose-Einstein condensate in quasi-1D. So just a side note, Luttinger liquid is an effective field theory that describes the low energy excitations of many generic one-dimensional interacting systems. In addition, we also realized a strongly correlated and highly excited metastable state that would be typically inaccessible in your traditional solid-state systems in contact with some thermal bath, because you would expect such highly excited state to relax very fast toward the low energy part of your eigenspectrum, so making them very difficult to investigate experimentally. So we accomplished this by performing a quantum quench of the contact or van der Waals interaction. And we observed that the relaxation of this metastable gas-like state depends strongly on DDI for our dipole polarization. Last but not least, I'll make connection of this metastable state to the novel phenomenon of quantum many-body scarring. So the many-body physics in one dimension is kind of strange because of our geometric constraint. In higher dimensions, we know that the Fermi liquid theory works quite well to describe many traditional solid-state systems. So under this scenario, our low energy excitations are essentially nearly free quasi-particles or particles stressed by density fluctuations. However, in 1D, we have the Luttinger liquid, where the elementary excitations are necessarily collectivized. So we can think of this by imagining performing a usual exchange operation between two atoms. However, because of the 1D geometry, you cannot do that without having them bump into each other. Therefore, the notion of quantum statistics is actually kind of intricate. In fact, both interacting bosons and fermions in 1D can be described by a basis of bosonic excitations. So this forms the basis of the field theory technique of bosonization, which is beyond the scope of this particular talk. So now, let's consider a bare-bone example of the Luttinger liquid, which is the famous Lipp-Integer model. So the setup is the following. We take n interacting bosons and arrange them on a line, and then impose periodic boundary conditions. So our Hamiltonians are shown here. In the first term, we simply have the kinetic energy in 1D. In the second term, we have the second term encapsulates the van der Waals or short-range contact interaction in the form of an effective delta function with a coupling strength C. So from now on, when I say C, I'm referring to the contact coupling strength in this Lipp-Integer model. So it turns out that this model is exactly solvable by using beta-Onsatz techniques. And in particular, when we have some intermediate repulsive C values, you get your familiar Fermi gas in one dimension. And then, if we follow by continuously increasing C toward an infinitely repulsive limit, you will start to observe this kind of n-type bunching effect that makes it look like a hardcore boson or almost like a fermion. In fact, in the infinitely repulsive limit, the bosons are said to be fermionized, leading to what is called a Tag-Schrodel gas. So to be more precise, if we consider the many-body wave function, this strongly interacting boson looks exactly like like that of a free fermion up to some proper symmetrization. If we consider the chemical potential, it is also exactly equal to the Fermi energy of our free fermion, defined in the usual way. And then this 1D strongly interacting Bose gas emulates fermion-like Pauli exclusion in real space, such that the local pair distribution, defined as shown here, vanishes at 0 distance. So that's the repulsive side of the business. So what happens when C is smaller than 0 or the interaction is attractive? So in fact, many of these lower lying states that the Hamiltonian supports are either soliton-like or many-body Carso state. So here I'm showing a cartoon of the two-body wave function of the absolute ground state as calculated by McBride back in the 60s. So you will notice that the amplitude of the wave function decays exponentially with the decay length scale set by the 1D scattering length, which is inversely proportional to C. So many of these states are unstable. So experimentally, what you would expect to observe is enhanced free-body heating or atom loss. However, there do exist metastable gas-like state in the high-energy part of your eigenspectrum, the lowest lying of which is what people call the super-Tamm-Schedel gas. And this particular excited state is accessible by quenching your C from the Tamm-Schedel limit for infinitely positive very quickly to the infinitely negative limit. And we can see how this works by examining the two-body wave function in this limit. So on the left-hand side, I have a cartoon of the ground state wave function on the repulsive side. So as we tweak up the interaction to be increasingly repulsive, you can see a cusp to form at 0 distance gradually. And this is what you expect if you observe fermionization. On the other hand, now let's look at the attractive side, the excited state. At infinite attraction, it actually is exactly the same as that of the Tamm-Schedel gas. And as we decrease the attraction slightly, exclusion volumes start to develop around 0 distance. And the length scale is also set by the 1D scattering length. And that is why a mental picture that you can think of when thinking about super Tamm's gas is that it's essentially a gas of hard rods. And because the wave function, and by extension the energy, comes continuously in a field limit, so this is why this quantum quench to a resonant sort of you would expect to couple dominantly from the Tamm-Schedel gas into the super Tamm's gas. And then you will also see that the state is metastable because there's very small overlap between these Coster wave function and the excited state wave function. And why is this state called a super Tamm's gas? So we can think of it in the sense of a density-density correlation function. And it has been calculated that it roughly goes as 1 over x2k in the large into liquid gas. And it turns out that for a Tamm-Schedel gas, k goes to 1. So the correlation pulls off as 1 over x squared. And you would expect interaction to modify this power law pull-off. And indeed, in the case of a super Tamm's gas, it has been calculated that k is actually smaller than 1. So making the fallout to be slower and hence more strongly correlated and super. And in the case of the Thomas Fermi gas, k is indeed greater than 1, which means the gas is less correlated. So now let's get to the actual experiment. So just to remind you, our scientific goals are first to realize the linear model plus a dipole-dipole interaction. And we would also like to explore this entire crossover diagram in both the ground and the excited state with the previously mentioned 3 extreme dipole polarizations. And the experimental ingredients that are required include a way to realize quasi-1D confinement, and we need to learn how to tune both BPI and contact interaction, and also specifically how to perform the quench to reach the super Tamm state. And then we'll need a diagnostic tool to directly control the density of state of our quasi-1D gas. And just as a refresher, this is the Hamiltonian of our system. So we have the kinetic energy, the contact interaction, as well as the pairwise dipole-dipole interaction. And as a preview, we'll tune C by the magnitude of the magnetic field, and we'll tune dVi by the pointing of our magnetic field. So first, how do we create quasi-1D confinement? So the setup is very simple. It's basically a 2D optical lattice. So how this works is that we take a pair of laser beams and then reflect them onto themselves, so as to create an interference pattern in both, in this case, Y and Z direction. So as a result, you have strong confinement along the two lattices, but then you have weak harmonic trapping in and out of the page or along X. And here I'm showing some parameters for the optical lattice expert in the audience. However, what you really need to pay attention to is consider the trap frequency. So the transverse, or Y and Z trap frequency in this case, is about 25 kilohertz, which is much, much larger than the trap frequency along the tube, which is only 40 hertz. In addition, if you consider the typical temperature scale of a gas of ultra-cold atoms, that would be on the order of 10 nanokelvin to 200 hertz. So that's also much, much smaller than our transverse trap frequency. So one could consider the transverse degrees of freedom to be effectively frozen. So therefore, we have a quasi-1D system along the tube. So here I'm showing a cross-section of our vacuum chamber. So you can see the two lattice beams as shown in the red arrows and the array of tubes here. And how we tune our dipole-dipole interaction is just simply by running current through two pairs of near Helmholtz coils. So to set our external bias field direction in the XZ plane and the dipoles which follow that pointing. So now, how do we tune contact interaction? In co-atoms in 3D, a well-known technique is by using the Fresnel-Feshbach resonance. So simply put, we know that the scattering cross-section is proportional to the 3D scattering length, or A3D squared. And the contact interaction is proportional to also A3D. So if we know how to tune A3D, we know how to tune contact interaction. And in a case, under a scenario of resonance scattering, one could in fact tune A3D and contact interaction from some positive values all the way up to infinitely positive, and then it swaps sign to infinitely negative across the resonance and to 0. So the analogous case under quasi-1D confinement is called the confinement-induced resonance. It is so termed because now there exists one additional relevant length scale in our problem, which is the transverse harmonic length, A perp, aside from A3D. So in order to tune C in 1D, so there are two ways. One is to tune A perp, but this involves changing the objects in some ways, which is less convenient. So indeed, we'll use the magnetic tune Feshbach resonance and enjoy this large tunability of 3D scattering length in order to change our C and to perform the quantum crunch as previously mentioned. And so now we need a way to be able to tell, okay, what equation of state do we have as we tune our parameters. So recall that along our 1D tubes, there is weak axial harmonic trap that serves to discretize the low-lying collective oscillation spectrum. So as a result, our first excited state, just as the animation shows, is simply the cloud center of mass oscillation, or the dipole Sawyer mode, at the trap frequency. So this frequency will only depend on the trap geometry, and it's hence not very interesting. So if you look at the second excited state, this is the oscillation in the width of our cloud, which is also called a breeding mode for obvious reasons. So the frequency of which would depend on both the trap geometry as well as interaction. So an intuition of this is that, okay, so the interaction would effectively change the stiffness of your gas in 1D, and then so it would respond differently as you sort of squeeze it a little bit. So here I summarize the crossover diagram in the ground state as follows. So the R is defined as the ratio square of the breathing and the dipole frequencies. So in a non-interactive limit, you would expect to see R equal to 4. As you tweak up C, you will reach the Thomas-Fermi region where R is equal to 3. And then as you tweak up 3 further, you fermionize your gas, and then you recover R equals to 4. A signature of having observed this strongly correlated superatomic gas is when you observe an R that's greater than 4. So indeed, the non-dipolar Lieb integer crossover diagram has been explored by the group of Christoph Negro at Innsbruck using cesium atoms. So here I show a summary plot of their data. On the y-axis, we also have the R parameter as defined. On the x-axis, we have the A squared interaction parameter that's appropriate for a weakly harmonically trapped system. So all you need to know is that the larger the A squared, the smaller the C. The smaller the A squared, the larger the C. So our confinement induced resonance, or CIR, will be when A squared is 0.
Well, do you have an intuitive reason why it becomes stiffer with like more correlations?
Yeah. It's kind of equivalent.
Well, why? Like, is there like an intuitive explanation why it becomes stiffer?
Okay, so I guess so the non-interacting region is kind of easy to picture because you would expect the excitation spectrum to be equally spaced. So it will necessarily happen at twice the sloshing frequency, right? And the time-necessary region, you would expect bunching, so it's sort of softer in a way. And then in the superatoms, you recall that we have the hard rod, so it's sort of some kind of anti-correlation. So it would oscillate faster because of spring constants. Oh yeah, right. So so in the Negro group's data, you can see that indeed. So they started out from the time-necessary regime, and then they started increasing C, and then fermentized the gas at roughly close to the CIR. And after performing the quantum crunch, switching the sign of the interaction from very large positive to very large negative, they observe indeed they have a superatomic gas because R is not greater than 4. And as predicted by the variation of Monte Carlo calculation, eventually when your gas is not as attractive, you no longer have a hard rod and you start coupling into the unstable quasi state, so your ratio starts dropping and eventually will go towards 0. So now let's first look at our data on the C is greater than 0 side in the ground state. So our C tuning sequence is as follows. So we'll start our BEC production in a time-necessary regime at some initial value of C. And then we'll change our field and by extension our C value somewhere over here without crossing resonance. So this is what we observe. So here I'm showing the same plottings R on the y-axis and X on the x-axis. And our collected oscillation data for all three dipolarization seem to be described quite well by the non-dipolar theory, which is shown in teal here. So we also try to account for the short-range dipole-dipole interaction. So this is the solid line in blue and red. And then you can see that the correction is quite minuscule and can't really resolve that in our experiment. So there is really kind of no surprise here. And now let's look at a more interesting regime where we perform the quantum crunch and try to produce a superatomic gas. So the RAM sequence is just very similar, except so we also start BEC production in the time-necessary regime. And then we quickly change our C across the confinement-induced resonance. And indeed, what we saw, so first I will show the magic angle for non-dipolar case. Much like Christoph Negro's, what they observed, we have initially R squared is greater than 4. And then eventually, at some finite C or A squared value, it starts falling down towards 0. However, what's different is in the repulsive dipolar case. So you can already see that the R is always greater or equal to 4 across all attractive interaction range. In the case of 0 degree though, it has a similar behavior as a 55 degree, except the crossover formation seems to have happened earlier. So if you always stay in one single gas-like metastable state, you would actually expect R to be always greater or equal to 4. So what's the intuition behind this collapse? So perhaps speculative mental picture we have is as follows. So here I'm showing a cartoon of the many-body eigenstress spectrum for a homogeneous Lipschitz system with only short-range compact interaction. So we have a bunch of these horizontal states with the energy that depends very weakly on C. So these are actually the gas-like state that I spoke of. And then we have these lower-lying ground states that depends very strongly on C in energy. So after the quantum quench, we will be on the C equals to minus infinity limit, and we will be in the lowest lying gas-like state. And as you tune C continuously, you might cross some of these degeneracy points. But because there is no gap opening, so your eigenstate actually is not mixed, so you expect to always stay in the gas-like state. However, in a realistic experimental system, you have both a harmonic trap, and then also in our case, you have a DDI. So this would serve to create avoided crossings for some of these degeneracy points. And then as you continuously tune C, you will expect your gas-like state to be mixed with some quasi-state characters. And as you go across many of these, eventually you might expect, okay, I have dominantly quasi-like states, and then there's collapse. So now let's look at our magic angle and attractive data again. So indeed, as C is tuned continuously across the CIR, you see that R initially goes above 4, and then drop down below 4. One thing to note is that R seems to approach that of the Thomas-Fermi gas, which is 3. And then in the case of the bound state or dynamic condensation, you would also expect the same result. So our hypothesis of the identity of these states is that they might be dominantly mechanically stable two-body bound states as predicted by this early theory paper using beta ansatz calculations. So more precisely, what I mean by that is the state can have negative energy because of the bound state, but it can also have a positive speed of sound, which would correspond to a finite positive compressibility, making it mechanically stable. And indeed, beyond this R approximately equal to 3 point, we observe enhanced heating, which is indicative of unstable crossover formation. So now let's switch gear and look at the more exotic data is equal to 90-degree data. So you see that R is always greater or equal to 4 across all attractive interaction range after continuously crossing the CIR. So it's quite surprising that this repulsive dipole actually prevent this highly excited state from relaxing. In addition, our collective oscillation data seems to be captured quite well by a non-dipolar figure that assumes exactly one excited state without relaxation. In addition, we also measure the energy density or energy per particle of this dipolar stabilized supertons gas. And this is done by simply performing ballistic expansion, releasing your atoms from the lattice. And then after long time expansion, you can extract the width of this expanded cloud along the axial direction, hence the energy density. So this also agrees quite well with the theory which is shown in teal here. So the y-axis is the energy density in some normalized unit, and the x-axis is a gamma interaction parameter, which you can just think of as proportional to C, the coupling strength. So now we have seen how this metastable state can relax versus our dipole polarization. One natural question to ask is what would the relaxation process be for one of these specific stabilized superton states? So basically, you look at the same Hamiltonian with the same C, same theta. So we designed the following experiment. So again, we start with some field value that corresponds to the repulsive side of the conforming-induced resonance. We quickly cross the resonance, performing the quantum quench, to some n field value, which corresponds to the attractive side of the CIR. And then we wait for a varying time delta t for the state to sort of evolve and explore the Hilbert space. And then we initiate the collective oscillation measurement at some t9. And then our observable will still be our ratio R. So we check that for a thermal state, and you should observe R is equal to 4. So this is verified by simply measuring our breeding frequency using a thermal gas at a temperature of about 200 nanokelvin, which is much, much hotter than what we have in our system. Actually, the subtlety in this measurement is that for each of these if you are not dumping boring spontaneous emission heating or whatever into your system, then you can consider this to be, for each of the delta T, it's like a different state preparation process that that your gas explores this constrained energy manifold. So the following, this is our data. So the first thing to notice is that, these light blue points, they are the average energy of our system versus delta T, and you can see it's roughly constant. And in terms of R, it starts with a superconstant value that's greater than 4, in fact about 4.7. And then it starts relaxing and eventually reaches 4 at about 60 milliseconds. Because we're not dumping extra energy into a system, we're always traversing within the same constrained energy manifold. So essentially what we've demonstrated is that there exists both thermal lag as well as a typical non-thermal state, which is a superconstant state, in this same energy manifold. And then we think that we can possibly make connection of this to the phenomenon of quantum many-body scarring. So first, let's understand this in a single particle scenario. So I will illustrate the concept by talking about the well-known configuration of a stadium failure, which sort of looks like this. So in a classical limit, this is a well-known periodic system, but then it is also known to support some unstable periodic orbits. One of them is shown here in this black line. If we consider the quantum mechanical limit, so at 0 time, so say if we initiate some wave packet that's centered around this classical periodic orbit, and then we just propagate it using Helmholtz equation with this periodic boundary, with the boundary condition imposed. And what you will notice is that the wave function, spectral wave, would actually be high around this classical periodic orbit, as if it's some sort of imprint or scar from the classical limit. However, this scar will heal if you take the limit as h bar goes to 0. So one way to see this is that, okay, so if you have a classical failure table and you shoot a ball out in this exact direction, then you will actually get chaotic behavior because this periodic orbit is unstable. So now we understand what single particle scar is. So it seems that physicists have been having difficulty generalizing the same concept to interacting many-body systems. One recent experimental breakthrough is the Harvard-MIT Caltech experiment of the 51-atom quantum simulator. So the setup is the following. So we have a chain of 51 atoms that could be independently initiated into either the ground, the dark red dot, or the Rydberg state, which is represented in yellow. So what they observed is that if you initiate this chain into some specific patterns, for example, this Z2 pattern, ground Rydberg, ground Rydberg, ground Rydberg, then the state would actually explore the Hilbert space in a non-ergodic fashion, even though, given this energy density, you would expect chaotic behavior. So this actually inspired a host of theoretical work in the community. However, the governing principle is still unclear today. We believe that perhaps our system can contribute meaningfully to this discussion in that, okay, so if you look at our Hamiltonian, it's clearly not a many-body localized system since there's no disorder involved. In addition, our Hamiltonian is also not just integrable, and this has been shown in our prior work of quantum Newton's cradle. Also, we've demonstrated for the theta equals to 90 case at least, we are able to prepare typical thermal state at the same energy density as some atypical non-thermal state, which is our supertungstic gas. So again, this atypical state exists amidst typical thermal states, which is kind of like, you have many chaotic states and some periodic trajectories. So we believe this is the first experimental scar-like state that is described and modeled in the continuum, which is different from this lattice spin model. So this is actually a lot more difficult to calculate theoretically, and so this demonstrates the power of quantum simulation. So I will conclude here. So today I've shown you the exploration of the crossover diagram of a Latinger liquid with both contact and dipole-dipole interaction. In the case of the C is greater than 0 in the ground state, as described described pretty well by theory up to experimental resolution. And more interestingly, in an excited state created by the quantum quint, we've seen that the repulsive dipole-dipole interaction stabilizes this metastable supertime state against cluster formation. And in the end, I've also shown you that this may indicate the realization of a novel quantum many-body Scarlet state, which is the first of its kind in our continuum model. So with that, I would like to thank my PI, Benjamin Lepp, and our theory collaborators, Seren Gopala Krishnan from the City University of New York, and my lab mate on the disposal experiment, Li Guanyu and Lin Guanyu, and then also the rest of lab, as well as these quantum agents. Thank you for your attention.
So I got a few questions and comments. One, in the 1D situations, you're actually, as you said, you're only quasi 1D.
Yeah.
And there are, if you do a perturbative expansion on the breakdown of the quasi 1D assumption, you're making contact with a theory that assumes 1D, but there's a little bit of 3D there. You get extra terms in the Hamiltonian that give additional nonlinearities, which in some cases are not so negligible. So I'm wondering, is that the case in you? I mean, how safely 1D are you? You gave this this nice ratio of oscillation frequency to temperature with like 1%, which seems pretty good. But I'm just wondering, do you expect to see any dirt from that?
Actually, one thing about this quasi-1D trapping is that you do not get the compound-induced resonance if you don't have the axial trapping. So that's sort of an indication of the remnant of sort of the 3Dness.
Yeah.
But then, aside from that, which is a feature rather than a bug. So aside from that, I don't really see any sort of obvious 3D behavior.
Follow to that. I mean, these is just going to sound like nitpicks, and it's I don't take this in the wrong way. It's just that, yeah. So the contact interaction assumption on the theory side also in the literature comes under question in the quasi 1D literature.
Okay.
So in other words, there's a cohort of theorists who simulate this stuff using computers who don't like to use the delta function contact interaction, and I mean, the results change when they put a little bit of width to that interaction. And so I'm wondering to what extent, I'm not sure that there's going to be any sensitivity, but there's a theoretical literature where people don't like that contact interaction.
Okay. So I think one experimental answer I can give is that, so we also try to characterize the position of our compound-induced resonance, which is based on this delta function 1D theory, and we don't really see any deviation from what you would expect from the calculation. So I think that sort of gives some confidence in our understanding.
One more question. So it's hard to measure. You say E over N is something that you want to use to make the energy divided by the particle number.
Yeah.
But in the 1D interacting situations, especially with attractive, because of the correlations between the particles, it's actually hard to know what the energy is. And so I'm wondering if you've, how you're making your estimates of E over N.
Oh, sure. So first recall that even though it's attractive, but we're in the highly excited state. So that's one note. And the other thing is so essentially we can calculate the density profile inside each of our tubes, and then we know the loading pattern into each of these tubes. So for each of those, we can extract energy value, and then essentially we take the ensemble average of that.
Even with correlations, like beta ansatz type.
Like we use beta ansatz.
You'll have binding energy that's going to make that. You see, just by looking at the distribution of atoms in your tube, that's not going to account for the correlation energy between pairs of atoms.
Well, beta ansatz included that.
We draw.
Yeah. So notice that was a time of flight measurement. we want
time of flight.
yeah, it's a time of flight measure.
Okay.
And also beta onset accounts for the interaction.
But experimentally, you may not know what state you're actually making. In this, you've got a lot of atoms in the tube, and they're correlating up in a way that may or may not make contact with the theory that you want to compare with. And so, getting that parameter energy, mean energy per particle, if you have sort of unknown correlations, it requires some level of inference. That's some.
So the tunneling rate between these tubes are very small.
Not the tunneling.
Right.
Yeah.
So just to put that out there. And then yes, and then before we started expansion to avoid unwanted collisions during this lattice deloading process, we actually tuned our 3D interactions length to be 0, so that our expansion we expect that to be below 0.
Okay.
Yeah.
Thanks.
We're a little bit over time, so if you have any more questions, we're saying about it. Let's give those speakers. 2 weeks from now, Vedika Kamani will be giving the last Q-Farm.